Okay. So stay with me with this language. So we're running graphs, and we'll be looking at trees as well. Okay, so depending on how rigorous you want to be, there are a couple of different versions of graph definitions. So I'll first start with the most naive one, the one that basically says what you see. But then you'll see that there are limitations to this definition. This is the definition is given in the book we use. So a graph consists of a set of elements denoted by V, called vertices, and a set E of, usually denoted E, of pairs of distinct vertices called edges. So there are two things, vertices and edges. So we usually represent a graph by drawing small black disk as a vertex, and by drawing lines between them. Okay, so we already drew some last time, but let me say on a vertex set 1, 2, 3, 4, 5, 6, you could take an edge set 1, 2, 1, 4, 1, 5, 2, 3, 2, 5, 3, 5, 5, 6. So when you have these two sets, you can draw a picture, and the picture will look like this. And the picture is not part of the data. So you can draw the picture by your choices. The data is just this, okay? So the picture is just a representation. So a graph is not the picture. In a clumsy way, you can draw it in a bad way. So when you have 1 and 2 connected, because we have this here, we have an edge, okay? So 1 and 4 is also connected by an edge. 1 and 5, 2 and 3. So we do not mind drawing it so that the lines cross. Because we emphasize the vertices with bigger dots, these things are okay. They don't mean that there's a vertex there, okay? Otherwise, you have to draw these each time, and it makes it uglier. So this means there's only edge between 2 and 3. This crossing doesn't mean anything, okay? I could have also drew it this way, but we don't talk about planar graphs. We just want to draw the graph. So 2, 5. You can also curve them a little bit. It's not important how the line passes through. Like you could say 3 and 5 like this. Doesn't matter how you drew it. 5 and 6. Okay? Just emphasize the vertices with bigger dots, and then you're fine. Now, there are two extensions or variations of these definitions. So variations Actually, this is in the book Grimaldi. This is discussed in more detail, in full detail. But one variation is you may want to keep track of which is the first coordinate. We often will not be doing that. Okay, when we say graph, these pairs will exactly mean equal to this. So they being pair does not mean anything to us. Okay, so when we say graph, we never will care about the direction. Okay, and when we draw, we will not draw directions. But you could define directed graphs as graphs where direction of edges are important, where the edges have directions. Now this we will not do because it's just for the things we discuss, this doesn't matter to us. Okay? So a directed graph will look like this, where edges will have directions, that you will have recording of which way is it. This is important when you have a passage only one way. Then your paths, of course, when you go 3, you have to go 1 now because you can't go through 4. But again, for the questions we discussed, we will not need directed graphs. So we will not discuss this. Okay? If you discuss directed graphs, for example, the concept of degree changes. You can have plus and minuses depending on if an edge comes towards you or leaves you. So you can record that information. So degree will be the difference of them. So many things are different. Let me use this so I don't go. But we will not discuss directed graphs, okay? Another variation, another extension of this concept is something called multigraph. This we actually solve in one of the problems. In Königsberg Bridge problem we saw this. Multigraphs will also appear in the minimal spanning tree problem. So in many places it appears, sometimes written like this, multigraph, sometimes together. But multigraph is a graph where multiple edges between two vertices are allowed. So when I'm doing, let's write it together. When we discuss some of these results, like Euler circuits or minimal spanning tree, I will be saying that let G be a graph or a multigraph. So we'll be allowing multiple edges between vertices. Now, if you want to allow multiple edges, then this becomes a little bit more interesting, right? You can draw the lines. You can even actually have multiple lines and different directions. I mean, most of you will probably prefer this version is the most general version, where you have edges and you have also multigraph. But there are some technicalities that makes this most general version a little bit harder to work. First of all, note that if you want to allow different vertices, different edges between vertices, suppose your vertices are indexed like this. You need to, you cannot use pairs anymore. If you say V1, V2, it will only mean one edge. But you want to mean many edges, right? So if you want to include many edges, now the definition of even graph changes. So now you have vertices, okay? In this case, one needs a slightly different definition, a more different definition. This is what I mean by definitions a little bit. You see that you can no longer talk about pairs of vertices as edges. You can have multiple in different directions. So in this case, you need to be a little bit careful what we do. Any idea what can solve this problem? Like, how can I approach to this general situation? Do you have a guess? Like, what should be the definition of, how should this be made into a theory? Any idea? And think about it. So, what you need to do is basically declare that you have a set of vertices and a set of edges, and just index them by themselves. Okay? So you say E1, E2, E3, E4, E5, E6, E7. And then give an extra information about how the edges are related to vertices. So you have source and target maps. Sometimes you can use initials or ends, where S takes E, any EI, one of these, to the vertex where it starts. Initial vertex is the vertex Vj if EI is from Vj to some other vertex. So basically it starts with Vj. For example, S of E1 will be V2. Okay, it's the source where it starts. And T is the target where it ends. You can use other letters. I mean, this is one theory, one book, something. So if Vi is Vk, say, then EI is from, say, W to Vk. So it ends with Vk. So target of E6 is V4. So you have not only the set, vertices, edges, but you have to also have these functions, which assigns for each edge a vertex as this initial or endpoint. So if you use this language of S and T, then, for example, some of these things we discuss can be explained using this language. This is more like Grimaldi's language, and this is the first one. This is more like Sheldon. This is from this thinner book that I use. And honestly, sometimes it's more convenient to have this simplicity as vertices being points and edges are lines between them. No directions, no pairs, nothing. No S and T functions. But then sometimes this is more convenient. We'll see why. So if I use that second, a sequence of edges, target of EI is same as the source of the next one. Is called a walk. Maybe I should also say, and the source of E1 is, say, V, and target of EK is W. Is a walk from V to W. Okay? So a walk is basically on your graph you given two vertices, so you want to go from here to here, V to W, you can use edges to go from there to there. So you can use this, 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 and this. This is a walk from there to there. Okay. Now here comes with a little bit ugliness with the terminology. There's many ways to go from there to there. You could go crazy things. For example, you could go like this, like this, like this, and go. This is also a walk. But in this walk, the second one, in the green one, you repeated this vertex twice. Where in the red one, no vertices were repeated. So sometimes this becomes an important issue. Which ones you want to allow vertices to be repeated in the walk? And on top of that, sometimes you can repeat an whole edge. For example, you could go like this and a couple of times turn around and go back here. So you can even repeat an edge. Okay? So in some walks, edges are repeated. And in some, even the vertices are repeated. I mean, as you can see, we talk about networks, we talk about connecting things. This could be a real life problem where you have some sort of network of banks in the Ankara region, in different banks by, say, Akbank banks. All the Akbank banks you could be having some sort of special line between two banks, and not every two banks may not have that line. So you could have a network of banks, Akbank banks in Ankara, where some banks have this connection between them through special line, where others are not. So you may ask, using this special connection, how they connect the Bilkent Akbank with Keçiören Akbank, using how many vertices. So this is a walk. This is what, walk doesn't mean you have to walk. It could be a network and connections and so on. On the break, we were talking about Facebook, for example. You can try to say, two persons on the Facebook, how can I connect them with common friends? And what's the shortest distance? So connecting them is a walk. And shortest distance is a walk which has minimum number of edges. So you can ask these things, very normally common things. So because this is semi important, there's a language for this. So this is a table from Grimaldi. You don't have to memorize it, but if you know this language, it will be good. So I said you can allow sometimes repeated vertices, and sometimes you can allow repeated edges. So this is the name of the walk. So open close I will explain in a minute, but let me first skip the open close version. So if you allow both of these, vertex repeated, edges repeated, what we call the bare thing is walk. Okay, so walk is something you go from V to W. Now, if that is the case when it's open, it's closed. So if it is closed, you call it closed walk. So closed means you have to come back to where you started. So V is equal to W. So closed means V is equal to W. So you start from V and W is where you end, and it's also equal to where you start. So walk and closed walk is very similar terminology. So you can see that we just call them walk generally. But now, if you don't allow edges to repeat, but you allow vertices to repeat. So for example here, you can repeat this vertex, but you're not allowed to edge. Now this is called circuit, because in electrical engineering you draw the circuit diagrams, right? And you have a lot of common vertices. So because of that, you should think this as circuit here. But circuit always is closed, right? So there's open version. I don't know why this terminology comes. Open version is trial. So remember the circuit, and hopefully we'll remember the trail. So trail is like circuit, but it doesn't have to close. Okay, so it's open circuit is called trail. Now, if you allow both of the repetitions, that means sorry, both of them are no. So if you now you don't allow like going around and around, and what kind of things you can think about? For example, you could have a big network graph like this. Okay, something like this. So for example, you may say, I'm going to start here and come back here, but I'm not allowed to repeat anything. I cannot even repeat vertices. So if you start here, if you cannot repeat vertices, it looks like this. Like it has to look like a cycle. So, I mean, you're not allowed to do this. Let me say it this way. You're not allowed to do this, for example. So you cannot repeat a vertex. Vertex then not be repeated. Okay. So if you do not repeat any vertex, something actually looks like a cycle. A circuit is a bunch of cycles. Think that way. A circuit is a bunch of cycles. We'll actually prove that later. But this is called cycle. And the open version is called a path. Path again, you don't want to repeat your... I mean, these things, they could be called apples and oranges too. I mean, some of them make sense, but a lot of it does just... People call them this way and it may not make sense to you, okay? Just this is the terminology. We have to use this terminology, of course. Okay. So I even forget some of them. So we'll look at the book if we need to make sure. These two use a lot more. So if you are going to, remember two, circuit and cycle is the two that's most common used. Now, if you so far we have been drawing graphs like this, but there is no reason a graph may look like this, where from this part you cannot go to this part by any edge. It could happen that you have components of your graph, where this component, this part, is not connected to this part. So now we'll discuss the language for connectedness. So to make this connectedness language, one has to, first of all, say two vertices are connected or communicate with each other. If you have a trail, a walk, or one of these. But if you have actually a trail or walk, you have also a path. So in the terminology, we only use the path. So two vertices on a graph, say V here and W here, we call them, they communicate if there is a path between them. And two vertices, say V and U, we say they don't communicate if they don't have a path between them. Okay, so this is our new terminology. Let U and V, W be two vertices on a graph. We say they communicate I sometimes call it connected. It's a little bit not a common language. This is more common, I guess. If there is a path between them. So it's either from V to W or W to V, there's a path. Of course, with no direct direction, paths also can be either way. A graph is called connected graph if any two vertices communicate with each other on the graph. On the graph. So as you see here, vertices here communicate with each other. So if I had only this part as a graph, this will be a connected graph. But together, this is not a connected graph. Because some parts here communicate with each other, but they don't communicate with everything here. So this whole thing is disconnected graph. So this is the language for connected graphs. Given a graph, say G as comma, the complement graph G or C is the graph with same vertices and EC complement graphs edges are exactly the pairs like IJ, where I and J are vertices, and I and j is not in edge. So a complement graph is the graph where edges are erased and any two vertices that didn't have an edge between them now have an edge between them. So you could sort of look at this. This is a graph G. It's complement graph. Now, none of these are edges. You cannot have edges between them. But any two vertex which didn't have edge between them now has to have an edge between them. Okay? So, like this. So we will discuss graphs and complement graphs in a more way, but so let me first say something about connectedness. So here we said this whole graph is not connected, but you have these components, okay? So whenever a graph is not connected, you can write it as disjoint union of components, okay? This is important. So let me write this here. For a graph G, and the vertex V, all the set of this the I need to stop. Let me say this in a few minutes. The language. Okay. I want to come to a very nice problem. Let me state the problem, and then when you're thinking about it, I will introduce more terminology. This was a final exam question last year. So just to give you a taste about what kind of questions could be challenging. So the question was, show that for any graph G, either G or G complement is connected. This was question that in the final. So you can see that even the simple things like this could be challenging. So here you see that they're both connected. So both connected is fine. But what we are saying that if one of them is not connected, the other one has to be connected. So for example, if I do a disconnected graph with 4 vertices, I have to have some way its complement has to be connected. So think about this problem when you're, but I will come back to this later, okay? Because I need to introduce something else. So what I want to introduce is this concept of connected component, and then we'll be done with connectedness pretty much. So given a graph G, V, and E as a graph G prime where you have V prime and E prime, this V prime is in V, a subset of vertices, and E prime is also a subset of E. Okay. is called a subgraph. So for graphs, you can talk about subgraphs. So given a graph, you can talk about a subgraph. So for example, you have a graph here. You can only take this part, and this will be a subgraph. Okay. So given a graph G and a vertex V, the subgraph of G, which includes all the vertices in G that communicates with V, is called the connected component of G for the vertex V, associated vertex V. So in some way it starts with V, or around V. So you have a vertex V, and it's sort of all the vertices that are connected to that, or communicates with V, is this subgraph. It's called the connected component of V. Now, I know you're writing it, but let me show in this figure. So for V, its connected component is this subgraph. For, say, U, the connected component is this subgraph. Okay? So you have components of a graph which is formed by this connectedness property. It's an important concept because many theorems we have will say we have a connected graph, or we'll say let's look at the component of this, connected component. So when we mean connected component, this is what we mean. Okay? So this problem is also solved using this idea, connected component idea. So in fact, every graph is a disjoint union of its connected components. So anytime we use the connected component language, you should always think that your graph is disjoint union of these things. Because, I mean, this actually comes from the language of equivalence classes. Okay, we have an equivalence relation here, which maybe you heard it, maybe not. But there's a equivalence relation here, and these are your equivalence classes. And equivalence classes make your set into a disjoint union. Okay, so I don't think we need to prove this, but just know that there is a mathematics which makes this more solid, which comes from equivalence classes. So these are equivalence classes of relation given by being communicating with each other. So we are basically making vertices equivalent to each other if they communicate, and then this is your equivalence class. Okay? So let's finish this solution of this problem, and then we'll have a weekend. I have 7 minutes. It's actually a very short proof, but you have to see it.
Hocam bahsettiğiniz o 6 connected olayı bu disjoint partlar için geçerli muhtemelen değil mi? Her bir disjoint.
Yes. If they don't connect it, then you can't even get from one to the other. Yes. So it's for the connected components. Any idea how to solve this problem? No, we can maybe do it in 5 minutes. Any idea, or should I write the proof? Okay, so if you want to show something is either, you just assume one of them and show the other one. Okay, so you assume that G is not connected, and then try to show that complement has to be connected. Now, if G is not connected, we know that it has connected components. Right? It can't be just one component. But if there are many components, which we don't care how many you have, it could be just two. There's always a line I can draw where this part does not communicate with this part. There's always a line I can draw where this part does not communicate with this other part. Okay, so imagine that this is Istanbul, and we don't have bridges on the Bosphorus. So then it may not be possible to get from some place to another by minibus on one side, but with no bridges, we know definitely that these people cannot go to that people without bridges, right? So think this as like Bosphorus. So there is no connection between this part and this part. And this is your graph, G. Now, the question is, so then there's a line that separates these two, this graph, into two subgraphs. Each of them may be connected or not, we don't care, okay? There could be more pieces here too, we don't care. But now we claim the complement graph is connected. How can you show the complement is connected? So which means if I take any two people in any part, any two, if I take any two, they will be connected with non-existing connections. So if any two people are not connected with anything, basically they will be connected by any non-existent connections. The complement means that. So for example, people who used to connect it with each other, they're no longer connected because there's no connection anymore. So you have to find ways to connect them with non-existing connections. The answer is very simple, actually. Just think about how you can connect people with non-existing connections. No?
Draw a line.
No, there's no line there.
Tüm connection'lardan exit oldu.
Okay, if V and W, they live across the line, if they're on the other sides, first of all, they must be connected by a non-existing line, right? Because they're not connected. So if they are on opposite sides in G, then they're connected. They're connected in complement graph. Okay, so what's left is if they're on the same site and they're possibly connected. How do you connect them?
Each one of them should be connected with every one of the other side.
Yes, exactly. There's at least one friend across, someone there. It's not empty there, which V is connected in the complement graph, and Z is connected on the complement graph. So that means you can, from W to V, there's a path, and then V to Z, there's a path. So W and Z is connected through this friend. Okay? If WZ are on the same side, then there is U on the other side, such that this W and U are in the edges of the complement graph, and U and Z is in the edges of the complement graph. So that means you have a path from W to Z. Then there's a path. Path from W to Z via U, through U. Okay? I mean, it's a very simple argument, but you have to get used to the terminology of graph theory and write proofs in it. The most difficult part of the graph theory is to write it in the right language of the graph theory. Otherwise, a lot of these are very, very naive logical arguments. But see, we wrote it so that it's mathematical. So you have to learn this language a little bit. I mean, this is the beginning. We will do this for a month, and after a while, you will get more used to it, probably. No questions, then I can stop today.